In this video, I'll look at some algebraic techniques for evaluating trig limits. One thing though, I don't want to lose sight of exactly what these trig limits represent. So let's start with a limit that we're familiar with. In the last video, we showed that the limit as x goes to 0 of sine x divided by x was equal to 1. Let's make sure we understand what this actually means. Imagine you took a look at a graph of sine of x. Okay, don't imagine. Just look right here. Okay, well, now imagine that you took your camera and you took a little snapshot of sine of x right near 0. And you made that region larger. Now imagine you did it again, but for real this time. You zoomed in as much as you possibly could on the function sine x until what you were looking at didn't look like a wavy sine curve anymore. What it looked like was a small portion of the line y equals x. That's what we mean when we say that the limit as x goes to 0 of sine x divided by x is equal to 1. We're saying near 0, sine x and x are indistinguishable from each other. That allows us to conclude that the limit as x goes to 0 of x divided by sine x is equal to 1 as well. Their ratio is 1, meaning near 0, the two functions are essentially the same. But what about other trig functions? How do they behave near 0 and elsewhere? Let's take a look at the limit as x goes to 0 of tan x over x. I'll start with a graph of tangent. And once again, we'll focus our attention on the function near 0. If you see the same result as with sine, you're right. Near 0, tan x also looks a lot like y equals x. In fact, we can show that the limit as x goes to 0 of tan x over x is equal to 1 using some algebra. First, I can write it as 1 over x times tangent of x. Then, I can rewrite tangent as sine over cosine. The product of those fractions can be written this way instead, sine x over x times 1 over cosine of x. Then, I can use the property of limits that the limit of a product is equal to the product of the limits. And at this stage, what I can see is that I have the limit as x goes to 0 of sine x over x, which we proved using the sandwich theorem, is equal to 1. And I have another limit as x goes to 0 of 1 over cosine of x that can be found via substitution. When I substitute 0, cosine of 0 is 1, and 1 divided by 1 is equal to 1. And so, this limit is equal to 1, just like sine of x over x. These two limits, the limit as x goes to 0 of tan x over x and sine x over x, are two of the three most important limits to know involving trigonometry. Let's look at the third. And that is the limit as x goes to 0 of cosine x minus 1 divided by x. So before I work this out, let me point out why it's cosine of x minus 1 over x and not just cosine of x over x. Recall that when you're trying to evaluate a limit algebraically, the very first thing to try is always substitution. When I try to substitute 0 into this limit, I have a 0 in the denominator, and I have a cosine of 0 minus 1 in the numerator. So that's type 0 divided by 0. 0 divided by 0 is an indeterminate form. It's something that needs further investigation. It indicates that there is a hole in the graph, in this case, the graph of cosine x minus 1 over x, and the location of that hole tells us the value of our limit. Sine x over x had a hole, and tan x over x had a hole. It just so happened that sine x over x and tan x over x had a hole right at y equals 1. We need to figure out where the hole is in this particular graph. It might be at y equals 1, it might not. Since substitution won't work in order to evaluate this limit, we have to try something else. Here's an idea. Let's try the conjugate. This technique worked well with square roots and also worked well back when we studied trig identities, so it's worth an effort. This changes our problem to the limit as x goes to 0 of cosine squared x minus 1 over x times the quantity cosine x plus 1. And cosine squared x minus 1 we'll recognize as negative sine squared. course, this gives us an idea of how to proceed. I can rewrite this limit as the limit as x goes to 0 of the product of these two functions, sine x over x times negative sine x over cosine x plus 1. The first, sine x over x, we already know that one. It is equal to 1, based off our proof from the sandwich theorem. Starting to see why that proof was very, very important to get things started. What's left is the limit as x goes to 0 of negative sine x over cosine x plus 1, and that can be evaluated via substitution. When I sub in 0, I get 0 divided by 1 plus 1, which is 0 divided by 2, or 0. And that means that the limit as x goes to 0 of cosine x minus 1 divided by x is equal to 1 times 0 divided by 2, or 0. So if we were to step back now and take a look at a graph of cosine x minus 1 near 0, what do you think we would see? Here's a zoomed out picture. If you were to zoom in near 0, would it look like the line y equals x, or would it look like something else? If you're saying it would look like the line y equals 0, you're right. Can you picture it? Let's look at a few other examples of trig limits that we can work out algebraically and that we can understand intuitively. A good example would be the limit as x goes to 0 of sine of 2x divided by x. This is an interesting example because there's a variety of ways that we can do it, both algebraically and intuitively. For starters, seeing sine of 2x might make you think of sine's double angle identity. If you think of it that way, you could rewrite the problem as the limit as x goes to 0 of 2 sine x cosine x divided by x. And this, of course, is a useful way to rewrite the problem because now I can say that this is the limit as x goes to 0 of sine x over x multiplied by 2 cosine x, a product of two functions, one of which we have done a lot of work on already, the limit as x goes to 0 of sine x over x. The other piece we can work out via substitution. And so we can see that the answer to this limit will be 1 times 2 cosine of 0. And since cosine of 0 is 1, our answer is just 2. That was pretty easy, but you might be surprised to find out there was an even easier way to solve this problem. Double angle identities are nice, but what would you have done if this was the limit as x goes to 0 of sine of 3x over x, or sine of 10x over x? A more general strategy might be multiplying by the fraction 2 over 2. Because now I can rewrite the limit as the limit as x goes to 0 of 2 sine of 2x over 2x. And this 2 right here in the numerator, the coefficient, can be factored out because it is not a function of x. And this will give me 2 times the limit as x goes to 0 of sine of 2x over 2x. And now, in a very, very sneaky step, I can notice that as x goes to 0, 2x goes to 0 as well. And what that leaves me with is 2 times a limit that I should be very familiar with, because this is the limit as the angle goes to 0 of sine of the angle divided by the angle. The exact thing that we proved was equal to 1 using the sandwich theorem, just with a change of variables. So this leaves me 2 times 1, which is equal to 2, and that was even easier. And it certainly bears repeating that it's easy to get lost in all of this algebra and miss intuitively what's actually going on here. And that's the idea that when I change the frequency of the sine curve, sine of 2x, sine of 3x, sine of 4x, well, sure, the wavelength is going to change. We're going to have a different period each time. But what's happening near 0? If we zoom in on that critical portion of those graphs, what we're going to see is going to look exactly like the line y equals 2x, y equals 3x, and y equals 4x. The interesting thing is this is not unique just to sine and cosine and tangent, but any curve, no matter how complex. If you look at it on a small enough scale, it looks like a piece of a line. And exactly which line Well, you could figure that out using limits and soon with derivatives.